So we found lengths of arcs with what we just did. And now we're actually going to see what would happen if we were to take that arc and then revolve it around an axis. And so that's what these pictures are right here. They've taken a length and they've revolved around this just being a line. And you see a line creates this cone shape. But if you take some other function, not a linear function, and revolve it, whatever the shape is, it's going to revolve. All right. So we're talking about surface area of that particular thing. If we were looking at a cone, like if you recall surface area, you would take kind of the base times the height, so to speak, if you were doing a cone. And so you would have the base being a circle and the height being, of course, a slant height. We had slant heights for pyramids. We had regular heights for cylinders, just depending on what you were looking at in geometry days. And so that same concept is where they come up with the definition or the area of the surface of revolution. So if you look at page 445, they'll show you written in terms of X or in terms of Y, depending on what it is. 2 pi r, that sounds an awful lot like the circumference, right? And then the height of it is the distance away. And so the r being the actual arc itself, that's how long we're going across. And the distance away from it is going to be this little r of x. And so we're actually using the same formula that we just did with bell work. The length of that arc there is going to come into play here. But you're going to multiply it by the function itself because the function determines how far away from the axis you are, assuming you're not shifted. And then 2 pi being part of the circumference formula. All right, so let's do some of these. Let's look at this first example. Find the area of the surface formed by revolving the graph f of x equals x cubed on the interval 0, 2 about the x-axis. All right, so we're taking this function, this cubic function here, from 0 to 1, 0 to 1, and we're revolving it around the x-axis here. All right? So our formula then starts out with our 2 pi. They've told us that we're going from upper to lower bound, or lower to upper bounds of 0 to 1. Now our r represents how far away we are from what we're revolving, all right? So at any point along this line here, I can tell how far away I am by my y value. Well, my y value is represented by the function itself. This function represents how far away from this x-axis I am, right? And so the r here is going to be my function. So my r is going to be the function they gave me. And then I'm going to use the formula that I use for the length of the arc itself, which is going to be the square root of 1 plus the derivative. The derivative of this particular function is 3x squared dx. All right? And so when I do this particular one, I'm going to simplify it, and I'm going to use substitution just like I would have before. So I'll simplify it first, which will give me 1 plus 9x to the 4th dx. And so let's look at how we get this particular one. So if I were to do u substitution here, my u value would be 1 plus 9x to the 4th. My du would be 36x cubed dx, right?
What makes it go from 3 to 9?
I squared it. I squared the entire thing. All right, I don't want a 36x cubed. I want just an x cubed. So I would say 1 over 36 du will equal x cubed dx, all right? And so if I do my u substitution, I would say 2 pi. And by the way, if you want to change your boundaries, you can. And then you don't have to go back to plugging your u back in. Do y'all remember that? So I can actually plug my 1 and 0 in here. And so I can say if I plug in a 0, that would give me a lower bound of 1. And if I plug in a 1, it would be an upper bound of 10. So you can do it that way, or you can plug it back in, whichever one you like better. So 0 to 1, if I leave it alone, I do need my 1 over 36. And then I would have my u, basically, to the 1/2 there, dx. Everything else is accounted for. X cubed dx, sorry, du, is accounted for with 136 du. My u is my 1 plus 9x to the 4th to the 1/2. So don't forget you can actually pull that 1 over 36 out, right? 2 pi over 36 or pi over 18. Antiderivative of u to the 1/2. That's going to be u to the 3/2 times 2/3. So this is going to be 2/3 u, and remember my u is 1 plus 9x to the 4th to the 3/2. And I'm going from 0 to 1. All right.
Where did 2/3 come from?
So I did, remember when you take antiderivative, you add 1 here. 1/2 plus 1 is 3/2. 1/2 plus 2/2. And then you divide by your new one, which is multiplying by the reciprocal. And then you can just plug all that in. You can cancel this, just make it a little more simple. So I have pi over 27. When I plug in a 1 here, I get 10 to the 3/2. Minus when I plug in a 0 here, I get 1 to the 3/2, which is just 1. And if you plug all of that into your calculator, you will get approximately 3.6. They took it to 3 decimal places, but that's about what you get. So if you look at this one, this is not the same as when we were doing like shell method or disk method. We are literally just taking that line, okay, and finding the surface area. So they have the formula x squared, which is just a parabola, right? They want it from 0 to square root over 2, which is just a beautiful range there, right? And we're taking about the y-axis. So now when I am talking about the distance from my area of revolution here, it's going to be a little different. When I looked at it from the other one, so when I did this one, I'm revolving around this axis. So the distance from my axis to the line is going to be my y value. Well, my y value is represented by the function x squared, or x cubed rather. Here, I'm revolving around the x-axis. So my distance from the x-axis to this here is just going to be my x value, whatever my x value is, right? I'm not talking about from here to the x-axis. I'm talking about from here to the point on the function. Well, the point on the function this direction is my x value, which is just represented by x, right? So when I do this formula, 2 pi, my upper and lower bounds here, my r of x is just going to be x here. My distance from what I'm revolving around to the actual curve is just x. So now this is not going to be the function, it's just going to be x, all right? And then this is still going to be my 1 plus f derivative of x squared, okay? So when you do these, you have to think about what am I revolving around? Do I need my y value, which would be my entire function as my r, or do I just need my x value, which is just the x value there, okay? And so I would set this one up like this. I would say 2 pi from 0 to square root of 2 of x, 1 plus, my derivative of x squared is just 2x, so I would put 2x here and square it. dx. And if I simplify that, of course I get something like this, 1 plus 4 x squared dx. Again, I can use u substitution, my u being 1 plus 4x squared, my du being 8x dx. I just want an x dx. So I would say 1/8 du is going to equal my x dx. And so for my u substitution, I'd have 2 pi times that 1/8 from 0 to square root of 2. And then I just want my u to the 1/2 du. And of course, the derivative of that looks very much like what we've been doing. My derivative would be, or antiderivative rather, I'm going to combine this right here to say pi over 4. Again, this is going to be 3/2. 1 plus 4x, no, not 3/2. 2/3. 1 plus 4x squared to the 3/2 from 0 to square root of 2. And I can simplify this as well. So I can have pi over 6, plug it in, square root of 2 squared is just 2, times 4 is 8, plus 1 is 9, to the 3/2. And then 0 is 1 to the 3/2. 9 to the 3/2 is much easier because it actually has a square root. So that's going to be 27. Or, yeah, square root of 9, yeah, is 3. Cubed is 27. Minus 1 would give me 26. So I get pi over 6 times 26. And then you can, of course, cancel those. 3 and 13. So we get 13 pi over 3.